Good morning from more like spring, New York City. The weather is getting warmer. The trees are beginning to bud. There are crocuses on the sidewalks, near the sidewalks, flower beds. And our little building here has a whole bunch of flowers just beginning to sprout because it's spring. Spring is in the air. We get springs earlier now. I watch the YouTube videos by my friend Bjorn Andreas Bull Hansen. He's in Norway. And one time when he made videos, it was all snowing around him. And now there's no snow there at all. And he said it's just getting warmer. All his videos now from Norway show, by the way, watch Bjorn's videos. They're very interesting. Bjorn Andreas Bull Hansen. When I clean the board, I'll put his name on the board. Let me do it now. Actually, I can't. There's no room. When I clean the board, I'll put Bjorn's name on the board. He mostly addresses his stuff to men, but women love it too because he's an easygoing guy. Anyway, I want to talk today about quantum gravity, not quite, quantum fields on curved space. All right. So what we've been doing is we've been working with quantum mechanics and quantum field theory. But all the time, in a situation whereby you could put down a grid, some people call these manifolds with a local patch, I don't want to get into that, where all the coordinates are flat. That angle is equal to that angle, this angle is equal to this angle. This is an old Euclidean theorem, that if you put two straight lines at each other crossing, this angle and this angle are equal, this angle and this angle are equal. And if you have two parallel lines, you can do more things. That's what's happening up here. Now when you have your regular Cartesian grid of coordinates, they're orthogonal. They're chosen such that those are right angles to make things easy. They're chosen so that, where are they? Covariant components, which are normal to the coordinates, can be automatic, right? But you can have contravariant components of a vector. A vector with covariant components, two normals written to the x and the y axis, if you like, and two lines which are parallel to the x and the y axis are contravariant components of, let's say, a vector or a tensor. Now I do have a lecture where I go into that, a little bit more detail, but that's the general idea. Now basically, this coordinate system is on a flat surface, flatland, like the little book. Everybody should read that little book from about 1880, I can't remember, Flatland. Everything is flat. However, in general, flatness only represents a local patch. Let's say on a huge sphere, the Earth is a sphere. If you have a swimming pool, right, and you look at the swimming pool, let's say it's a 100-meter long Olympic swimming pool, and there are no ripples on it, it's dead flat, it's just sitting there. You say, oh, that's flat. Well, it's only locally flat because if you made that swimming pool bigger, if you extended it, let's say to London, you would notice the curvature on it. That swimming pool is obeying the curvature of the Earth. Whatever curvature that is, as a way of working it out, is there in that swimming pool, but it's so tiny you don't notice it. What we say is the space is locally flat, but on the grand scale it's curved. So, curvatures and gravity. Quantum gravity, I don't think there is such a thing as a quantum theory of gravity. I think it's very much like trying to quantize a sound wave. A sound wave is a kind of a statistical ripple in molecules. A sound wave in air, I mean, because in a metal you can quantize sound waves. Phonons are the things in there. But that's different because we're talking about a rigid body in a metal. In a gas, the air, sound waves in air, you cannot quantize them. They're statistical little ripples. So what we can do for gravity is this. We can say, well, gravity represents the background against which things happen. What could happen? Quantum mechanics could happen. Quantum electrodynamics could happen. Now, when we're talking about field theory, we looked at the Klein-Gordon equation. And we derived the Klein-Gordon equation. you can go back and look at that. I'm just dealing with the Klein-Gordon equation because it's a simple example. What I'm going to talk about is quantum fields on curved space. In other words, all the stuff that happens, quantum electrodynamics, quantum chromodynamics, the standard model, all the various different fields can be written in a background whereby the coordinates are not flat, they are curved. See? Now to get curvatures, we just look at the derivative. That's really all we do. The derivative becomes a covariant derivative. This is without indices. The derivative becomes a covariant derivative, which is the derivative plus another piece. Actually, it's very much like differentiation following the motion in fluid dynamics, right? You differentiate locally, but then there's a general rotation as well. So these curvatures change the setup. What happens is the metric becomes more complicated. And you end up with the Reimann tensor. Now I've done a lot of this in my lectures on general relativity, 1 to 14. You might want to look at those. You don't need it for this because I want to give a general idea of quantum fields on curved space. So we go from flat to curved coordinates. Look at the coordinates. They're curves now. They could be big parts of a sphere. They could be great circles. It could be any kind of random thing. But we'll draw tangents to those curves. There's a tangent to the curve, look. So we can have our covariant coordinates or our contravariant coordinates. Covariant or contravariant coordinates with respect to tangents to our curved coordinates. So look at for two things, you need to look at where I derive the Klein-Gordon equation. I derive it just using the definitions of momentum and energy as we do in ordinary low energy quantum mechanics. And we arrive at the Klein-Gordon equation. This block notation I don't like. It's really d mu times d mu, which can be written like this. The metric times the two covariant derivatives, where this d mu is more complicated. I will get into it in a minute. So we write the Klein-Gordon equation with curvatures in the derivatives. This whole thing to do with curvatures complicates the whole equation. But we still have an m squared phi. Now usually when we have quantum fields on curved space, for various reasons, to get technical, this term crops up. But for our demonstration, I'm going to set the epsilon 0. Epsilon, curvature, phi. I'll set this epsilon 0 because I want to keep my presentation simple. Now what we do is we choose a set of coordinates which are very special. Locally they're flat, but globally there are curvatures that start showing up. They're called Reimann normal coordinates. So I take Reimann normal coordinates, g mu nu becomes the flat space plus the curvature part. And then we can go to higher order terms in these y's. These y's are the normal coordinates. Normal, yes, normal. So the g mu nu downstairs looks like this with a minus sign in front of the curvature part. And the g mu nu upstairs looks like this with a minus sign, with a plus sign near the curvature part. Because when these two things apply together, we have to get a delta mu nu. Now what do the Christoffel symbols look like? If you don't know what Christoffel symbols look like or what they are, you have to go back to my general relativity lectures 1, 2, 3 and 4 at least. I do them very, very simply. Christoffel symbols, after Christoffel about 1860, I can't remember. But I do it in my lectures. So we substitute all these results, this one, and this one, into this equation, okay? Now, that's all I can say for this part of the board. To continue, I need to erase the board. But before I do that, I want to talk about some of the guys who did this great work in the past. First of all, there is Leonard Parker and David Toms. Parker and Toms. This is the mother of all papers. I think it's the greatest physics paper ever written. It comes after, this is 1983, it comes after another one by Bunch and Parker from 1979, where they work out the Feynman propagator in curved space, a momentum space representation. I'm going to begin showing you how to do this kind of stuff. But they do it, it's much more complicated because they actually have the Green's function, and that's really where you get the propagator from. But they're the Reimann normal coordinates to higher order, and then they go into momentum space. This one, Parker and Tom's, is the mother of all papers. I mean, it's phenomenal. Even in the appendix, if you wanted to derive this equation, where is it? C15, I think. Doesn't matter. This one here, I think. If you want to derive that, that takes about 100 pages. Just that one right there. Now there are many other papers. I have Dinjo O'Connor's thesis, which he gave me a long time ago, which is in quantum fields on curved space from 1985, and he does a similar sort of a thing. He's using the Schwinger-DeWitt expansion. However, if you want to learn quantum fields on curved space, there's nothing to beat the old paper that I did myself with Bellucci in 1990. So it's 30 years old, wormholes and charged particles. You can ignore the wormholes and just learn how to do some quantum fields on curved space, where I do everything out explicitly using the Schwinger-DeWitt expansion. I haven't said what that is, but it's a very useful technique. And I work out the renormalization group equations. I did all that by hand. That was my first paper years ago. I did it with Bellucci. And there are many other papers that I could talk about. I wonder will I? I won't talk about papers. There are two standard books, neither of which I went through. But if you wanted to save yourself work, you could go through Birrell and Davies' Quantum Fields in Curved Space, which is a classic. Stephen Fulling, Aspects of Field Theory on Curved Space, also a classic. Both of these will get you on the road to understanding quantum fields in curved space. So that's all I'm doing for this part of the presentation. I'll close up and erase the board.